Hi all. In today's video, we will discuss solid design principles. Designing robust, scalable, and maintainable software system is one of the core responsibilities of a software architect. The solid principles, coined by Robert C. Martin, serves as a foundational guide for object-oriented design that promotes low coupling, high cohesion, and code that's easier to test, extend, and maintain. These principles don't just help individual developers, they guide entire teams in building architecture that can evolve with business needs. Whether you are designing microservices, enterprise applications, or monoliths, Solid lays the groundwork for flexibility and long term sustainability. In this video, we'll explore each solid principle using real world examples, UML diagrams, and Java based design patterns. This will empower us to make better design decisions across our teams and architecture. So let's start with single responsibility principle. The single responsibility principle, or SRP, states that a class should have one and only one reason to change. That means every class should do only one thing. It should have single responsibility. In the image, we can see that we are having a loan processor class and here it has multiple responsibilities. If a class handles too many tasks like business logic, printing reports, and saving to DB, it becomes hard to maintain. So in our case, the loan processor class is hard to maintain. To divide it in three classes with different responsibilities like printing loan details, loan processor, and saving to database, will make sure that we are following the principle of one class and one responsibility. Single responsibility principle is important because it improves readability, it is easier to test, it also reduces bugs when making changes, and it supports clean architecture. The main power of SRP is clean, maintainable, testable code. If one thing changes, only one class needs to change. Now we have seen how the single responsibility principle keeps classes focused and modular. Let's move on to the open close principle, which is a key to building systems that can grow without breaking existing code. The open close principle says that a software entities, classes, modules, and functions should be open for extension but closed for modifications. This means you should be able to add new behavior without changing existing code. Existing classes should be stable and untouched. This helps prevent bugs and support scalability. The right way to do is to extend the code via interfaces, abstract class, or composition. So in the example on the screen, we can say that here in loan approval services, all the functionality is at one place. We need to divide it in such a way that we'll be having loan approver as an interface, and whatever functionality we want to have, we will have it as personal loan approver, home loan approver, etc. This will be our service class. That's the main concept of open close principle. Our classes should welcome new behaviors without breaking what already works. Next, we need to understand what is Liskov substitution principle. LSP defines that subtypes must be substitutable for their base type without breaking the program. Basically, in simple word, it means that if a class B is a subclass of A, then object of A should be replaceable with object of class B without changing the desirable behavior of the program. So in the example, we can see that we are having a card interface and we are having credit card and debit card. This is our main class or client code by which we'll be calling the code of credit card or debit card. So in the second example where violation of LSP is done is, for example, if we are having a gift card and it does not behaves similar to the debit card and credit card. So it means that it will do some different functionality than we are having in our existing credit and debit cards. We can pass either a debit card or credit card and the behavior is predictable. Here we can see in the code, the behavior here will be predictable and there will be no exceptions as well. So this is the main concept of LSP or let's go substitution principle. On the similar lines, we should be able to make sure that we also follow interface segregation principle. Now, interface segregation principle says that clients should not be forced to depend on interfaces that they do not use or they don't want to use. In simpler terms, don't make a big fat interface as we can see here on the screen. We need to break it down into simpler and role specific interfaces as we can see on the screen. So the classes implementing them only implement what they actually need. So in our example, this is a big fat interface of bank card with is having multiple methods like withdraw, deposit, swipe. Instead of that, we will be having multiple interfaces like this, which will be responsible for handling one specific feature like withdraw, deposit, swipe, online transactions, etc. And for example, if we are having an ATM card which implements withdrawable and depositable interface only, that means withdrawable and depositable interface only. We don't have to forcefully implement these two interfaces. In real world, we can think of a TV remote which has button for volumes, channels, power, and AC remote which has temperature control, fan speed, etc. But we don't give all the controls in same remote. This is called interface segregation in real life. Basically, interface segregation helps to avoid God interfaces. Break functionality specific contracts in interfaces like we can see on the screen. And our classes stay clean, focused, and free from unnecessary code. The last principle is dependency inversion principle. The definition says that high-level modules should not depend on low-level modules, and both should depend on abstractions. Abstractions should not depend on details. Details should depend on abstractions. In other words, we can say high-level classes like service, business logic shouldn't directly depend on low-level classes like DO, utility class, or DB drivers. Instead, they should depend on interfaces or abstract classes. That is abstractions. Basically, we need to create abstractions here. Think of charging your phone. Your phone is a high-level module and the wall socket is a low-level module. But if your phone was hardwired to Indian-style sockets only, it wouldn't work abroad. But using a universal charger and interface, you can plug into any socket. This is the simplest example. To understand it in technical language, we can say we are having a class which is having feature of SQL database. Now, in our order service, we are directly connecting the MySQL service through MySQL database. But instead of that, we can create an interface which will be having a method connect. Now, here we'll be having one more layer which will be called MySQL database implements database class. Now, here we can have order service which can depend on this class to derive whatever kind of connection it wants. If we want post PostgreSQL database connection, then this class will be changed. If you want MongoDB database connection, this class will change. So basically, we are changing this interface, and low level modules are not depending on high level modules. Basically, the, basically, when we use this, it makes system extensible and testable. We can also observe that high level business logic shouldn't know concrete implementations like order service. Whatever we are doing in order service should be independent of the whole program. It should execute independently. It follows the program to interfaces and not implementations. And basically, it enables dependency injections, which Spring heavily uses. So these were the 5 solid design principles which we need to use in order to develop any applications. This will make sure that our architecture and code are in consistency with the whole of our application. That's all for today. Thank you.